So let's get started. Today is going to be the final lecture on divide and conquer, and it's going to be my final lecture for 3 weeks or so. Professor Chiesa will start lecturing next week, Tuesday. So today what we're going to do is look at the fast Fourier transform, as well as polynomial multiplication. Okay, so let's start with polynomial multiplication. So what we're given as input is two polynomials, each of degree less than d. So we're given a of x, which is equal to a0 plus a1 times x plus plus a d minus 1 times x to the d minus 1. And we're also given as input a polynomial b of x, which is b0 plus b1x plus plus b d minus 1 x to the d minus 1. Okay, so the input is basically two vectors of these coefficients. So we're given the coefficients ai's as well as bi's. And the goal is to compute the vector of coefficients of C, which is A times B. Right? So C C of x is C0 plus plus C. What's the degree of C? Well, it's at most 2d minus 2. So C2d minus 2, x to the 2d minus 2. And henceforth, I'm going to define n to be 2d minus 1. Okay, so C is a polynomial of degree less than n. Okay? I can also interpret a and b as also being polynomials of degree less than n. In fact, they have degrees roughly n over 2. But I can think of these as all being three polynomials of degree less than n, right? Where for a and b, half the coefficients are 0. Okay? And just a reminder, right? So what are these CIs? Well, it's some kind of convolution. Right? So C0 is A0, B0. C1 is A0, B1 plus A1, B0. In general, CK is the sum over J goes from 0 to K of AJ, BK minus J. Make sense? Where if k is large, like if k is bigger than d, like let's say k is closer to n, I'll interpret, like there is no, for example, let's pretend that k is 1.5d. Then the first summand here would be a0 times b 1.5d. But b is only a degree less than d polynomial, right? There is no 1.5dth coefficient. But I'm just interpreting that as 0, right? Because I pad a and b out to degree n minus 1, and all those later coefficients are 0. Does that make sense? I can interpret all these three polynomials as degree less than n. Okay. Okay, great. So, questions? That's the problem we're going to study. Notice that polynomial multiplication is related. Oh, is that in the way? Okay, let me move it. Better? Yeah? Okay. Notice that polynomial multiplication is very closely related to integer multiplication, right? Because if I wanted to multiply integer multiplication, if I wanted to multiply, say, 1074 times 2351, this is my, let's say, alpha, and this is my beta, I could define polynomials. A of x is 4 plus 7x plus 0 times x squared plus x cubed, or 1 times x cubed. And then b of x is 1 plus 5x plus 3x squared plus 2x cubed. And then alpha times beta is just a times b as polynomials evaluated at the point 10, right? Right? Alpha is just a of 10, and beta is just b of 10. So alpha times beta is just the product polynomial evaluated at 10. So these things are very closely related problems. Okay? Now, if you had, I mean, granted, if someone gave you an algorithm that was fast that did polynomial multiplication, you still have to do a little bit of work to turn a times b. Like, that algorithm will give you a times b, right? You still need to do a little work to turn that into what is alpha times beta. And why is that? What's a one-word reason for why? Or a short answer for why? An algorithm that solves polynomial multiplication, when you ask it to compute a times b, what does it give you? It gives you the coefficients of the product polynomial, right? This would be a capital C. The point is the coefficients might be bigger than 9. Usually when you write an integer down, you write it in some base like base 10, you want to know the digits of the product integer. The digits is it's a string of numbers, digits that are between 0 and 9. But when you get the product polynomial here, some of the coefficients in the product polynomial might be bigger than 9. So you still have to then do a little bit of addition and keep track of carries. Okay, so there's a little bit of extra work you have to do to turn the product polynomial into the product of the two integers, but you can see that these are very closely related problems. Okay, great. So now let's talk about algorithms for doing polynomial multiplication. So algorithm 1 for polynomial multiplication, is the so-called naive algorithm. Basically use for loops. So you loop over k, right? You loop over the coefficients of c that you want to compute. And for each coefficient of k, you then just do this formula, which itself is another for loop. Okay? So two nested for loops. How many entries are there of c? How many coefficients are there? There are about n of them. There are exactly n of them. Each one of these summations involves at most n terms. Okay? So two nested for loops of size n, this is O of n squared. Okay? So maybe I'll just beat this point to death a little bit, just once. The argument that I just gave you shows that it's at most n squared, right? Because I said the for loop has n terms in it, and each one involves a sum of size at most n. So the fact that I said at most means that I gave an upper bound on the runtime of big O of n squared. It doesn't imply that it's theta n squared, because to say that it's theta n squared, I would need to say that the runtime is at least proportional to n squared. But that's also true, right? And the reason that's true is, yes, it's okay. So the point is, there are some sums here that don't involve n terms. Like getting C0 doesn't require summing over n things. There's just one product you have to compute. C1 only requires a constant number of additions as well, or flops as well. But once you get to like somewhere in the middle, like Cn over 2 and onward, each one of these, computing Cn over 2 requires omega n flops. And computing the next one also requires omega n flops. So for half of the coefficients of C, you're doing at least n over 2 work. So your total work is at least n squared over 4, which is omega n squared. It's also omega n squared, since computing each of, let's say, Cn over 2 all the way to Cn minus 1 requires at least n over 2 flops each. So therefore, we have the big O, we have the omega, so it's theta n squared. Right? So this implies your work is at least n to the 4, n squared over 4, over 2 squared flops, right? N over 2 squared. Let's write it like n over 2 squared. Okay? Does that make sense? So just be a little careful, like when just because you showed an upper bound doesn't mean you showed theta. The upper bound means big O. If you want to show theta, you need to show that you're doing at least some amount of work. Yes? Oh, yeah, that's right. That's true. So maybe what I'll say is instead of Cn over 2 to Cn minus 1, I'll just say Cn over 2 all the way to C3n over 4. Okay. So then each one of those requires at least n over 4 flops. So I think now you have n over 4 squared. Does that sound better? Yeah.
What if most of the coefficients are 0? Then theta n squared doesn't apply to it, right?
Okay, great. So what if most of the coefficients are 0? So just usually in this class, when we talk about the running time of an algorithm, we fix some input size. So like here it's n. And I'm sorry, I keep switching between capital N and lowercase n. I guess I said they're all capital. But what we mean when we say like T of n is the runtime on inputs of length n, we mean if you fix n, T of n is the worst case input, the max over all inputs of size n of the runtime for inputs of that input. Okay? So yes, there are some inputs that are easy because most of the entries and most of the coefficients are 0. But T of n is defined for me to be the worst case runtime over all inputs of size n, in which case it really is theta. Okay, great. Right. So by the way, just in case not everyone caught the comment there, basically what he was observing was that Cn minus 1 is also a really small sum, right? It's equal to a d minus 1 times b d minus 1. So it doesn't involve actually summing n things. But I think I fixed that now. Okay, yeah?
In this kind of algorithm, can we consider like optimization? Like, can we consider a condition where if this is a 0 value or something like that to speed up the process? Or is that like...
Yeah, I mean, you can do that. You're saying, can I write code that does if statements and says, if it's a nice input, if it's sparse, it has mostly 0 coefficients, I'll do something else. Yeah, you could do that. But you're still, I mean, what if that if doesn't hold? Your worst case runtime will still be omega n squared, right? Okay. Okay, great. Good. So can you do better than algorithm 1, the naive algorithm? And by the way, today I know we obsessed like basically up until now, we've been obsessive about kind of bit complexity or of arithmetic algorithms, right? Addition is not constant time, I always said. Addition takes time proportional to the number of digits. Multiplication is not constant time. It takes time proportional to like n to the log base 2 of 3 if you have n digits. For today, I'm just going to count flops, okay? I'm not going to deal with the complexity of actual like basic arithmetic like addition and multiplication, okay? That's just for today. Yes?
So if we're counting flops, would it have been a sufficient argument for theta then squared if we took the way in which the c's increase in complexity from c to 0? And couldn't we have argued that this is just a sum of consecutive integers?
Yeah, you mean you could have So you could have computed exactly like it took me about one flop to get C0, more than 2 to get C1, more than 3 plus 4 plus 5 plus 6, which is also theta n squared. The beautiful thing about, I guess, arguments like this is that you don't have to do you don't have to think as much. Like you don't have to do any closed form summations, but you could. By the way, I encourage you, anyone who did not look at the homework 1 solutions, I encourage you to look at the solution showing that log of n factorial is theta n log n. So you could use Stirling approximation, right, which was one of the hints in the problem. You could also just do something much sloppier, which works, right, which says, well, you're multiplying 1 up to n. Half the numbers there are at least n over 2, right? So n factorial is at least n over 2 to the n over 2. So log of that is omega n log n, right? So that's like completely first principles. I didn't need Stirling. So it's useful for you, I think, to become comfortable with these kinds of arguments because, yes, you could use Stirling. It's just more math, right? And maybe you don't remember Stirling. But the argument I just gave you took me like 5 seconds to deliver, right? And these kind of sloppy arguments that lose constant factors are good for you to know because you can like quickly access what the answer is without having to think too hard, okay? Which is kind of the same argument I did here, right? I didn't do a closed form summation, which I could have done. I just said something like, well, at least a quarter of the entries require at least n over 4 work, so it's omega n squared, right? I could have done a closed form summation, gotten pretty much the same thing up to a constant factor. It would just required more thinking. Okay, great. So that's algorithm 1. Algorithm 2, you could still do Karatsuba's algorithm. Okay? Right? So the idea there would be I write a of x as a0 plus a1 x plus dot 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 plus, let's say, an minus 1 x to the n minus 1. Or let me say, x to the n minus 1. Right? Most of these are 0. I do the same thing for b. And then I just divide kind of the coefficients in half, right? So I say there's this thing here, and then there's the second half of coefficients. And then I say that this thing here is like a low times x, and this thing here is a high times x times, let's say, x to the n over 2 or something like that. And then I do the same thing here. And then I get that a times b is equal to a low times b low plus x to the n over 2, a low b high plus a high b low plus x to the n, is it? I guess most of these are going to be 0. So a high. Once you recurse down one, or I could have done d, but once you recurse down, they're not going to all be 0 anymore. Ah, bh, right? And then again, they're kind of the naive way would be you have to do 4 recursive multiplications, but then if you do the Karatsuba trick, you only have to do 3, and then you get n to the log base 2 of 3. So it's completely the same trick. Okay? So can we do even better? And the answer is going to be yes. That's the topic of today's lecture. And it's going to be yes via an algorithm called the fast Fourier transform. And before I cover the fast Fourier transform, I want to tell you where it's coming from. Okay? It's coming from basically interpolation. So interpolation, polynomial interpolation says any degree less than n polynomial is determined by its evaluation on n distinct points. Right? So you can tell me what C is by telling me its n coefficients. But you can also uniquely tell me what C is by telling me what C of n distinct points are. So like what C evaluated at 0, that's a number. What C evaluated at 15, that's another number. If you tell me its evaluations on n distinct inputs, that list of evaluations uniquely determines C. Okay? And why is that? Well, the reason, one way to see it is linear algebra. Okay? So why is this the case? Let's say that our distinct points are x0, x1, up to xn minus 1 are distinct points. And let's call this polynomial C, okay? I can write down some matrix vector multiplication. So let me do the following. I'll write here 1, x0, x0 squared, all the way up to x0 to the n minus 1. All the way down, and then here I'll put 1, xn minus 1, all the way to xn minus 1 raised to the n minus first power. Right? So all the rows look similar. It's like 1, xi squared, all the way up to xi to the n minus 1. And here I'll put a vector, which is the vector of coefficients, which I don't know necessarily. But whatever this polynomial is, it has n coefficients, which are the coefficients of x to the 0 all the way up to x to the n minus 1. And you're telling me that you know what the evaluations are on n distinct points, and these evaluations are, let's say, y0 up to yn minus 1. Right? So what we have here is an equation which looks like, I'll just call it VC equals y. Right? We have some kind of matrix vector equals vector equation here. So what does linear algebra tell you? Well, if I want to know what C is, isn't C just V inverse y? Okay. Well, it is if what? If V is invertible, right? This V, maybe it's not invertible. So V's that look like this, that have this format, they can be expressed as 1, x0, x0 squared, etc. Okay, these are called van der Waals matrices. Sorry, it's one word even though I ran out of space. Van der Waals is one word. Okay. If I wanted to check whether a van der Waals matrix is invertible, what do I need to check? Or what's one way to check that a matrix is invertible? What? Sorry? Determinant, right? Check to make sure that the determinant of V is not 0. It's invertible if and only if its determinant is not 0. And there is a theorem, which I'm not going to prove today, this is not a linear algebra class, is that the determinant of any van der Waals matrix is the product over all I less than j of xi minus xj. Okay? That's just the theorem we'll take for granted in this class. Right? So the point is, if all the xi's are different, all the xi minus xj's are non-zero, you're taking the product of a bunch of non-zero things, it's non-zero. Okay? Great. So that's why this interpolation theorem is true, why C is uniquely determined by its evaluation on n points. Okay? So now what are we going to do? Well, the beautiful thing is, to know the evaluation of C on one point doesn't take n squared time, it only takes n time. Right? Because we don't actually have to multiply a times b as polynomials to know what C is evaluated at a point. Right? Because, let me write this down. Yes, it's true that C is equal to, C of x is equal to a times b as polynomials evaluated at x. But it's also equal to a of x times b of x. Right? So we don't actually need to multiply a times b. We can just evaluate a. Well, this chalk is getting all over me. We can just evaluate a, evaluate b at that point. Now we have two numbers, and we just multiply those numbers together. How long does it take to evaluate a at a single point? N time, or d time, right? People believe that? Anyone not believe that? You don't believe it? Okay, right? So, so if I wanted to define a function, eval, that takes a polynomial p of, let's say, degree less than n, and evaluates it at a point x, I can say something like answer starts off as 0, and let's say my current pow is 1, and then I say for, let's say, I equals 0 to n minus 1, answer gets increased by pi times cpow, and then cpow gets multiplied by x. And then I return the answer. Right? There's a linear time algorithm to evaluate a polynomial at a point. Okay. Linear time in terms of number of flops. Yeah. Question?
I think you just answered that. I was going to ask, what are you assuming takes on?
Oh, yeah. For the entire duration of this lecture, a flop is constant time. Any addition, multiplication is constant time. Okay. Okay, great. So the point is I can evaluate A in linear time, B in linear time, one more flop to multiply them. So overall, linear time to get the evaluation. So now if I wanted to plug this into this idea of interpolation, right? So the point is now I can get, what is y0? Y0 is this dot product. Just, by the way, I guess maybe I should have waved my hands at this to make sure you see what I'm doing here, right? Y0 is the dot product of the 0th row with C. What is that? That's C0 times 1 plus C1 times x plus C2x squared plus C3x cubed, etc. Right? Each one of these dot products is the evaluation of C at that point. So y0 is the evaluation at x0, y1 is the evaluation at x1, etc. Each one of these evaluations, I just said on that board, I can get in linear time. I need n of them. So overall, it takes me n squared time to get all of these n evaluations. That doesn't sound like progress because algorithm 1 was already n squared time. And what's worse is that now I need to go from the evaluations to C, right? I need to actually solve this linear system. How do I solve for C? I have to compute V inverse. Okay? Which, I mean, in general, I can invert a matrix using Gaussian elimination. That takes cubic time. Okay, so now I'm spending n cubed time to do the interpolation method. So it's even worse than algorithm 1. Okay. So this all sounds like a terrible idea. Okay. And this is where the fast Fourier transform comes in. Okay. So the fast Fourier transform, I just want to make sure we're all on the same page in terms of types. I hate type errors, okay? If you remember, you should remember, I guess, you should remember everything in this lecture, but if you don't remember everything, if you choose to only remember some of this lecture, remember the following types. So types, the fast Fourier transform also known as the FFT, is an algorithm. Okay? Whereas the discrete Fourier transform also known as the DFT, is not an algorithm. It's a matrix. Okay? So the fast Fourier transform is an algorithm to quickly multiply by the discrete Fourier transform. Okay? That's what the FFT does. The FFT is an algorithm. So the discrete Fourier transform is some matrix F. I'll tell you what it is in a second. And the FFT is an algorithm which, if you give me a vector x, it'll return to you f times x, where f is some matrix that I'm going to define in a second. Okay? So these are two, they have different types. Okay? And I told you the DFT is a matrix. In particular, it's a Vandermonde matrix. Okay? So the DFT does correspond, multiplying the DFT times C does correspond to evaluating C on n different inputs, on n different points. What are those points? Okay. So the DFT matrix, F, it's an n by n matrix. Fjk, okay, so actually this is going to, so okay, Fij, let's say, is equal to omega to the ij. Or I'll write it as omega to the I raised to the j, which is the same thing as omega I to the ij, where omega is defined to be e to the minus 2 pi times the square root of minus 1 over n. So this is the n by n discrete Fourier transform. So this, yeah, so I know this is usually called I, but I feel like using I to index things, so I just explicitly wrote square root of minus 1. Okay? So what is the, why am I doing this? Where's this all coming from? Okay, so I want to explain that. Luckily, we have a lot of time. This whole lecture is on FFT, okay, so I can draw pretty pictures. So just remember, complex numbers review. Okay. A complex number, let's say Z is a complex number. I can think of Z in one of two ways. I can think of Z as being A plus the square root of minus 1 times B. Right? It has the real and imaginary part. I can also think of Z as being R times e to the square root minus 1 times theta. So this is like the difference between Cartesian and polar coordinates. If you want to see a picture, let's draw a picture. So let's say that Z is A plus square root of minus 1 times B. Well, here's A, and here's B, and here's Z right here. That's my point in the complex plane. So there's one way of picturing Z. But the other way of looking at Z is, well, let's draw the line segment from Z to the origin. And the length of this line segment is the radius, right? So I guess this is like Euclidean geometry, right? So this is A, this is B. So R is the square root of A squared plus B squared. And then there's some angle here, theta, right? So R is just the square root of A squared plus B squared. And theta is just tan inverse of B over A. Okay. So these two ways these two things are identical ways of thinking about Z. Okay. If you haven't seen this before, e to the square root minus 1 theta is cosine theta plus square root of minus 1 times sine theta, which is why this thing works. Okay, great. So now going back to why are we picking omega this way? So let's just back up a little bit. What are we really trying to do? We know that if we're going to use this interpolation approach, we had better find a Vandermonde matrix V such that there's a fast algorithm for applying V to C. Right? We want a Vandermonde matrix that is somehow special so that even though most matrices we need to use like n squared or n cubed time to multiply by the, or I guess n squared, matrix vector multiplication time is n squared, right? using for loops. We want there to be something very special about the van der Waals matrix we're choosing that lets us have an algorithm that can go faster than n squared. And it's going to be a divide and conquer algorithm, as you probably guessed, because we're still doing divide and conquer. And what I want to show you is that this choice of van der Waals matrix, this discrete Fourier transform, does lend itself to a fast algorithm to do the matrix vector multiplication. Okay? So what is this omega? Let's say that n is equal to 8. Let me draw omega to the 0, omega to the 1, all the way up to omega to the 7, which is n minus 1. So we have let's draw the plane, the complex plane. I said one way of thinking about complex numbers is the radius times e to the square root of minus 1 times theta. So notice here, there is no r, right? It's like e to the square root of minus 1 times some angle, right? So all of these numbers lie on the unit circle. They all lie in the unit circle. What's omega to the 0? Omega to the 0 is just 1. So this is omega to the 0 right here. And what's my angle theta? My angle theta is 2 pi over n. Or in fact, here I guess I made it minus 2 pi over n. Actually, let me just change it to plus. It doesn't really matter that much. Ooh. Ouch. Okay, that bled. Okay. Oh, no, it didn't bleed, but it probably will. Okay, so let's make it plus. So what's the angle? The angle is 2 pi over n. N is 8 for me, so that's pi over 4, right? So the angle is 45 degrees. So this is omega to the 1, right, at 45 degrees. This is omega squared. This is omega cubed. This is omega to the 4th. This is omega to the 5th, omega to the 6th, etc. Omega to the 7th. And then omega to the 8th just wraps around. So what you get are points that are equally spaced around the circle. Okay? That's what these points are. These points, this is my x0, x1 up to x7. x0 is omega, sorry. xi is omega to the I. Right? These 8 points are my xi's over here. Okay? So now, let's think about, now I have some polynomial, okay, that I want to be able to evaluate on all n of these points. So let's say I have some polynomial p as degree less than n, and I want p of omega to the I for all I. Okay. So what I want is, let's say p of z is p0 plus p1z plus p2z, etc., plus pn minus 1z. What am I saying? P2z squared, pn minus 1z to the n minus 1. Okay, I'm lucky. It's still not bleeding, so it's probably not going to bleed. Okay. I can write this as P0 plus P2 z squared plus P4 z squared squared, etc. These are basically the even indices, plus P1 plus P3 z squared plus P5 z squared squared plus dot 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 times z. And I'll call this P even. And I'll call this P odd. Okay? So what I've just said is that what I've just said is that P of Z is equal to P even applied to the point Z squared plus Z times P odd applied to the point Z squared. So this implies, in order to obtain P evaluated at the points omega to the 0, P omega to the 1, all the way up to P omega to the n minus 1, we just need P even applied to omega to the 0, P even applied to omega squared, and then P even applied to omega to the 2n minus 2. And similarly, P odd applied to the same points as well. Okay. So if you parameterize by n, what we're saying is to evaluate a degree at most n polynomial on n of these points, you twice need to evaluate a degree. What's the degree of P even and P odd? N over 2. You twice need to evaluate a degree at most n over 2 polynomial on how many points? On n over 2 points? On n points. Well, I mean, it's going to be n over 2, but I mean, it's not clear immediately, or maybe it is, right, if you're thinking ahead. I basically just took all the previous endpoints and squared them. That's all I did. I used to have endpoints. I still have endpoints. They're just the squares of the previous points. So yes, I did decrease the degree of the polynomial that I need to work with, but have I decreased the number of points that I'm working with? Well, it seems maybe not, but now let's look back at that picture. Okay? And this is the magic of choosing these. These are called, by the way, roots of unity. Right? Omega is an nth root of unity. It just means that if you raise it to the nth power, you get 1. Okay? So what is? So let's look at omega. Let's look at omega to the 0, omega squared, omega to the 4th, etc. So omega to the 0. Basically, I want to look at the squares of all these endpoints. So let's look at the square of that point. Omega to the 0 squared is still omega to the 0. That's this point. Let's look at omega 1 squared. Omega 1 squared is omega to the 2. That's this point. How about omega 2 squared? That's omega to the 4. Omega 3 squared is omega to the 6. Omega 4 squared is omega to the 8. Omega to the 8 is 1, because it's the root of unity, right? So that's just this point again. Omega to the 5th squared is omega to the 10, but omega to the 8 is 1. So omega to the 10 is just omega squared times omega to the 8, which is omega squared, which is this point, which is omega squared. Omega to the 6th squared is omega to the 12, which is the same thing as omega to the 4th. And omega to the 7th is omega to the 14th. Omega to the 7th squared is omega to the 14th, which is the same as omega to the 6th. So what this tells me is that when I square all the points, I basically get only half the points doubled up. So, in fact, it is true. When I take these roots of unity, there are n of them, and I square them all, I only have n over 2 distinct points now. In fact, I have the n over 2th roots of unity. So I have basically done some kind of reduction, right? Moving from evaluating degree at most n polynomial on n points, I now only have to multiply or evaluate a degree n over 2 polynomial on at most n over 2 distinct points. And they themselves are also n over 2th roots of unity. They're exactly, basically that n became n over 2. So it's exactly the same problem of half the size. And I'm doing it twice. Once for p even and once for p odd. Right? And once I have those evaluations, I can easily combine them. Right? Because if I want, remember, there's divide and conquer. So I divide, I solve the recursive subproblems. But now I know p evens and p odds at these points. What I actually want to know is I want to know p at those points. Right? But that's easy to get because once I know p even and p odd at those points, p at some point, p at the point, let's say omega, cubed, or omega, p at some point x is just p odd at that point times that number itself plus p even at that point. Squared. Right? So once I have all the evaluations of p odd and p even, just with one more multiplication and addition, I can combine those two evaluations into what p is. And there are n of them, so I need to do that n times. So I can write down now a recurrence relation. The number of flops it takes to apply a degree at most n polynomial to these nth roots of unities, right? Omega to the 0 to the 1 all the way up to omega to the n minus 1. Well, I have to do it twice for polynomials of degree at most n over 2, namely p odd and p even. And then I need to do, well, some theta n work to combine the results. Okay? And I'm going to assume n is a perfect power of 2 so that it makes sense to keep having n without worrying about round off. And I can do that by basically just padding the polynomial to make its degree 1 less than a power of 2. Right? So if its degree was actually 6, then I'll just add 0 times x to the 7th as an extra term, and now its degree is 1 less than a power of 2. Right? I'll just basically round the degree to be 1 less than the closest power of 2. Okay. And if we want to be pedantic, this is the case when n is bigger than 2 or bigger than 1. And when n is equal to 1, basically it's just, I guess, 1. Okay. And we know what this solves to. Well, 1 by the master theorem, but 2, you've already seen this multiple times before. This is the same exact recurrence as merge sort. Right? So this implies that T of n is theta of n log n. So in a number of flops that's proportional to n log n, instead of n squared, I can evaluate a polynomial on these n different points. I can get all the evaluations. Basically what that means, and that's the same thing as saying I can multiply by the DFT in n log n flops. For all x, I can compute f times x, where f is the DFT matrix in n log n flops. Okay. Questions about that? Yeah. How do you get the distribution of omega on the circle? What do you mean by how do you get it?
I mean, it's homogeneous, right?
Omega is defined to be that number. Omega is that complex number, right? So just looking at this view of complex number, I can think of a complex number as a radius times e to the square root of minus 1 times some angle, which is exactly what that looks like, right? So r there is 1, and the angle is 2 pi over n, which is this. And then omega squared, it's now 4 pi over n, etc., right? So I just move around the circle. And I saw another question, yeah.
What's the extra work done by converting the original polynomial to a complex plane?
What's the work done by converting the original polynomial to the complex plane? I'm not converting the original polynomial at all. I'm just assuming that I can do arithmetic on, well, I'm assuming I can do arithmetic on, let's say, complex numbers in constant time, but that's the same as assuming I can do arithmetic on real numbers in constant time. Because, a complex number I can write this decomposition. Like I can treat it as a plus square root of minus 1 times b. But if you want, for today, even assume I can do flops on complex numbers in constant time. I'm just counting flops on complex numbers for today. Okay? In reality, that's kind of bogus because complex numbers and real numbers have infinite precision, right? So I can't even represent them exactly on a computer. In reality, what you would do is you would run this algorithm with like floating point. So you'd have some rounding errors. And if you want to be fully rigorous about it, you would do some analysis to argue like how much precision do I need in my computation to get the answer up to some desired precision. But I'm not going to focus on those precision issues today. Yeah.
How do we know the coefficients p survive? Aren't the coefficients of multiple polynomial?
How do we know that the coefficients of p survive?
P sub I.
Of p sub i?
Yeah. Isn't that
Oh, yeah. Okay, good. So right now I'm only talking about, remember before I said like, we know that interpolation works because we have this thing vc equals y, therefore c equals v inverse y. So right now all I'm talking about, so right now v is f, right? The Van der Waals matrix I'm using is the DFT, so that's f. So all I'm telling you is how to get, so let's just back up for a second. This is good to remind ourselves of what we're trying to do here. What's the game plan? Right? The game plan is remember, at the end, what was the beginning problem I started this lecture with polynomial multiplication? I'm given a polynomial a and a polynomial b. I want to compute c, which is a times b, right? So we're given polynomials a and b. So step one, compute f times a to get, I don't know, give me a letter. What? J. No, I don't like, J is to me an index. So Fourier transform of A. Okay. And how am I going to do this? I'm going to do this using the fast Fourier transform, which is the algorithm we just discussed. This algorithm is called the fast Fourier transform. Okay? This divide and conquer algorithm is called the fast Fourier transform. So I'm going to compute f times, I'm going to linearize the coefficients of A into a vector. That's the vector A. And then I'm going to apply the DFT matrix to that vector. And I can do that quickly using the fast Fourier transform. And that gives me the right-hand side. Remember VC equals Y? This is Y. Right? This is V, this is C, this is Y. Okay? And then step two, so A hat there is a vector. I'm going to compute f times b to get the Fourier transform of b. That's, again, another f of t. Right? So now I have the evaluations of a on n different points, namely omega to the 0 all the way up to omega to the n minus 1. This a hat is the evaluation of a on n different points. This b hat is the evaluation of b on n different points, namely omega to the 0 up to the omega to the n minus 1. Now what do I want to know? I want to know the evaluation of c on those points. So I'll compute C hat j to be A hat j times B hat j for j going from 0 to n minus 1. Right? So now I have the evaluation of C on those endpoints. And that I can do in linear time now, because it's just n multiplications. Right? Does that make sense? But what I actually want is I want the coefficients of C. I don't want the evaluations of C on these n minus 1 points. By the way, this is called this is called the Fourier transform, or the discrete Fourier transform of A. This is called the discrete Fourier transform of B, et cetera, if you ever see that. But for us today, it's just the evaluation of A on those special endpoints. What I actually want is I want to know C, not C hat. What did I have to do to go from the evaluations back to the original coefficients? Multiply by the inverse. So I'm going to return F inverse applied to C hat. How do I compute F inverse applied to C hat? Okay, so now we need to understand that. What is F inverse? So claim F inverse is just 1 over n times F bar. What do I mean by bar? I mean complex conjugate, entry-wise. Right? So people remember complex conjugate? Reminder. Z bar, going with that view of Z, Z bar is equal to A minus the square root of minus 1 times B. Or going with the other way, it's R times e to the square root of minus 1 times minus theta. So you do the angle in the reverse direction. Or think of it as 2 pi minus theta. Okay? So for us, basically, right, so the point is, I guess I deleted the circle, but if you think of omega, omega is like you go this way, counterclockwise with angle 2 pi over n. So the complex conjugate of omega is you go clockwise with angle 2 pi over n, which is the same thing as omega to the n minus 1. Okay, so proving this claim is not that much work, but I don't want to do it because, as you will see on Monday, it's going to be some part of one of your homework problems. Okay, so you'll do that on your next homework. Okay, so now what that says is so I can replace this with F bar times C hat 1 over n. Okay, so that's what that says. That's by that claim. But we spent all this lecture talking about how to multiply by F. The FFT lets you multiply by F. It doesn't necessarily let you multiply by F bar. So then, I guess another claim, or last claim that we need, is that this is just true of matrix vector multiplication with complex numbers in general. If you have a matrix A, and you bar that matrix, and then you want to apply it to a vector V, that's the same thing as applying A to the bar of V and then barring the result. Does that make sense? Okay. So this just means entry-wise complex conjugate on the vector V. And then I'll apply A to that vector. That's a vector. And then I'll bar that output vector. So what this tells me is this thing is the same thing as 1 over n times F applied to C hat bar, and then I bar that. Okay? Barring this vector is, again, linear time. I just go through one by one in this vector and do complex conjugate and all the numbers in it. Now I apply F to that. F is the DFT. I know how to do that. That's just the F of t. Now I get an output answer, and then I just bar that answer. So at the end of the day, I do 3 F of t's. Right? I do F of t on A, I do F of t on B, I pointwise multiply the outputs, then I do a complex conjugate entry-wise on that output, and then I apply another FFT on that, and then I bar that. Okay? And now I have C. I have the coefficients of C of x. Okay? So in 3 FFTs plus a linear amount of work, I can do polynomial multiplication. Questions about that? Uh-oh. Yes. Sorry, say it again. We can do what?
We can divide n by 2 and still get an integer because n over 6 should be a degree of the polynomial.
Yeah.
What if it's not up to the n degree?
Yeah, okay, so the question was, we're assuming here that we can divide by n by 2 and get an integer. What if n is not even? So again, I can assume without loss of generality that n is a power of 2, right? So this is what I was saying earlier, just by basically padding out the polynomial by putting a bunch of 0 coefficients. So without loss of generality, n is a power of 2. And this is actually a case where that's important. Like, I did that for convenience. You could talk about the same thing for algorithms like merge sort. Merge sort, you keep saying I'm going to divide it into, etc. Like, what if n is not a power of 2? The truth is, in merge sort, you can make the analysis work even if you just like divide it as evenly as possible. So, if n is actually 15, just make 1/2 be 7 and 1/2 be 8. It'll all work out. You can prove that formally. Okay. Here, you actually need n to be a power of 2 to make the algorithm work. But you can guarantee that by padding zeros on the polynomials. Okay? So in the beginning, before you run the algorithm, pad a bunch of 0 coefficients and make n be a power of 2. Yeah? So don't think of C hat and A hat and B hat as polynomials. They're just numbers. Right? C hat is a vector. C hat is a vector of length n. So C hat sub j is a number. Okay? A hat of j is a number, B hat of j is a number. This is just a product of 2 numbers, and I assume that I can do a flop in constant time. Forget about, so you asked questions about like, in Fourier transforms, why can I do pointwise multiplication, blah, blah, blah. Forget whatever you know about Fourier transforms, okay? All that you need to know right now is I evaluated a polynomial on a point. That point happens to be omega or omega to the 5th or whatever. But I evaluated the polynomial a on the point omega to the j. That's what a hat j is. A hat j is what was the evaluation of the polynomial a on the point omega to the j. This is some number. What is the evaluation of the polynomial b on the point omega to the j? That's some other number. And then c hat j is what's the evaluation of the polynomial c on the point omega to the j? Right? But as I said earlier, whenever you have polynomial multiplication, c of x is equal to a times b evaluated at x, but that's the same thing as a of x times b of x. Right? So I can just take the evaluations and multiply them together, and that gives me c of x. So that's all that's happening here. Okay? Any other questions? Yeah.
If our original encoding in terms of points relies on the fact that we can get the polynomial back with degree plus 1 point, different points, right? But we're evaluating it at roots of unity, which have, 4 different values?
Sorry, wait. I don't think I fully understood the question. So we needed to be able to evaluate the polynomial on n distinct points.
Right. So what I'm wondering is, if we only have so few values that keep repeating, why don't we end up with repeated points?
So the point is, in the beginning, we had these n equally spaced points on the circle. This was like 1 omega squared up to omega to the n minus 1. And then when we recurse, basically half the points, when you square them, it becomes like a 2-to-1 mapping, right? So instead of like, it was like 0 degrees, 45, 90, 135, 180, etc. Now it's like 0 degrees, 90 degrees, 180 degrees, 270, etc. And then when I do one level deeper of recursion, I get 0, 180, and that's it. And then when I do one more level deeper of recursion, I just get 0. But But maybe we can take this offline because we don't have a lot of time left, and I do want to say one more thing. Okay, but yeah, ask me offline. Okay. So let's say the last thing, we still have 15 minutes left. I want to say one more thing before I let you out, and then we're done with divide and conquer. So it's not a prereq, but just show of hands. Who here has taken 16a? Oh, a lot of people. Who's not taken 16a? A decent number of people. Okay. So for those of you who have taken it, and even for those of you who haven't, you will maybe at some point take it. If not, that's okay. You might have heard about this cross-correlation, I think, that was covered at some point in 16a, right? Wait, did I hear size or something? So cross-correlation. I, for whatever reason, call it successive dot products. It's the same thing. So the idea here is you have two vectors of different lengths. So let's say you have a vector x, which is x0, x1, up to xm minus 1. And then you have a longer vector y, which is kind of y0, y1, up to yn minus 1. And what I want to know is kind of what's the dot product between x and the first m entries of y. Also, if I shift x over by 1, kind of what's the dot product of x with the next m entries of y, etc. Does it make sense? Basically, for each shift of x, I want to take it down here and take the dot product of y, right? So I want to know the sum I goes from 0 to m minus 1 of xi, yi. I also want to know the sum of xi, I plus 1, I goes from 0 to m minus 1. I also want to know the sum of xi, yi plus 2, I goes from 0 to m minus 1, etc. I want to basically know all of these shifts of x with the dot products of shifts of x with y. Right? This is a list of how many numbers, I guess, n minus m plus 1. N minus m plus 1 numbers. Right? Now, the naive thing would be I just kind of have nested for loops. Right? So for each shift, I calculate the dot product. That dot product takes like m flops. There are n minus m plus 1 shifts. So in total, my running time is like n minus m times m. Right? So the naive algorithm is like, and I'll think of n is for me like strictly bigger than m. So this is going to be something like theta n minus m times m time. Just using nested for loops. And if you think of n as much bigger, like let's say n is bigger than 2m, this is like nm time, right? Because n minus m is at least n over 2 if n is really big, and then that's basically nm. So the question is, can I do better using the fast Fourier transform? Okay, as you probably guessed. And since I'm talking about it, that means the answer is probably yes. So faster algorithm via fast polynomial multiplication, which we just saw you can do using the f of t. Okay. So what am I going to do? I'll define a polynomial y of z is going to be y0 plus y1 times z plus dot, 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 plus y n minus 1 times z to the n minus 1. I'll define another polynomial x of z, which is going to be backwards. It's going to be xm minus 1 plus xm minus 2 times z plus dot, 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 plus x0 times z to the n minus 1. Okay. And then I want to compute, I guess y times x should be z, but no, z of z is not very pretty. Okay, so let's call y times x q. And let's say q is defined to be y times x. So basically the product polynomial. So let's say q of z now is basically y times x of z, which has some coefficients, right? It's q0 plus q1z plus dot, 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 plus q n plus m minus 2 z to the n plus m minus 2. Now let's think about what are these coefficients. So q0 is going to be basically, what's the definition of polynomial multiplication? You look at a monomial here and a monomial here such that their exponents add to 0. So that's just, here's a z to the 0, and here's a z to the 0. These are the only two monomials whose exponents add to 0. So you get y0 x to the m minus 1, xm minus 1. Okay, that doesn't look very interesting. Let's fast forward to, question? No. Let's fast forward to the, I guess, qm minus 1. So now we have to add in the products of all coefficients corresponding to monomials where the exponents add to m minus 1. So here I have z to the 0. So I need a monomial here that makes 0 plus that exponent add to m minus 1. That corresponds to z to the m minus 1. What's z to the m minus 1's coefficient? It's y m minus 1. So the coefficient, so here I'm going to have xm minus 1, ym minus 1. That's my first product. What about when I have, so here this is z to the 1. If here the monomial is z to the 1, here it's going to be ym minus 2 is going to have monomial z to the m minus 2. So plus xm minus 2 times ym minus 2, right? Plus all the way down to x0, y0. So this is exactly the first successive dot product I want, or the first cross correlation I want. And you can work it out yourself. If I look at, so basically qm minus 1 gives me my first cross correlation. And as you might guess, qm minus 2 gives me the next one, etc. Okay? So basically, I'll return as my cross correlations qm minus 1, qm, all the way up to, I guess, q. How many of them are there? I'm going to be off by 1 because I'm really bad at arithmetic. But I guess the point is I should add n minus m. So all the way up to, I think, qn minus 1. Yeah? So those, unless I'm off by 1, I hope I'm not, those should be n minus m plus 1 numbers. And those numbers, those n minus m plus 1 numbers are exactly the n minus m plus 1 successive dot products or cross correlations. Okay? And again, so how long does it take me to compute this? Well, n is the bigger degree, right? I said n is bigger than m. Maybe I need to pad n to be the closest power of 2, but it's only going to at most double n. And then I do the FFT, right? Or actually, as we saw, I do 3 FFTs. Right? And then that's going to take me a total of n log n time. Okay? One last takeaway I want you to remember before I let you go is if you have a black box that lets you quickly multiply by the DFT, such as, for example, the FFT, you can use that black box. You don't need to know how that thing works. I mean, I showed you how it works today, but you don't need to know how that thing works. So you could use it as a subroutine inside an algorithm that solves polynomial multiplication. And if you have an algorithm that solves polynomial multiplication quickly, you can use that as a black box to solve successive dot product. Okay? So when you see a problem on an exam, right, people believe in abstraction barriers, okay? So when you see a problem on the exam and you realize, hey, I can solve, or on the homework, and for example, hint, there is a problem that's going to come on homework 3 where you might want to think about successive dot products, okay? If you see a problem where you realize, hey, I can solve this problem given a subroutine that solves successive dot products, you can just say that on your solution. You can just say, here's the vector x I'm going to set up based on the input. Here's the vector y I'm going to set up based on the input. Now I'm going to apply successive dot products to x and y, and voila, I have my answer. In your solution, you never have to say FFT. You never have to say polynomial multiplication, okay? Because that's, to me, an abstraction violation. Those are black boxes that are inside of this algorithm that solves successive dot products. But now that you know you can solve successive dot products, you don't need to talk about the inner workings of it, okay? The only time you need to talk about FFT, or the only time you need to talk about polynomial multiplication, is when you're actually doing polynomial multiplication and you're not doing successive dot products. Okay, then it matters how you set up the polynomials. Okay? Or you only need to talk about FFT when the thing you're doing really is multiplying by the discrete Fourier transform matrix. Okay? If all you're doing is polynomial multiplication, you don't ever need to say the words FFT. Right? You can just say, now we do fast polynomial multiplication as we saw in class. Does that make sense? So please respect the abstraction barriers. Okay.